Okay, so we have two topics remaining essentially here. So we have unstructured data, and after that we will talk about some cloud services. So we talked about structured versus unstructured data. We talked about databases yesterday. So just to reiterate, databases usually when we are talking about storing data, we are talking about storing them in relational data tables. This means that the types of data and everything need to be structured. They need to be organized. We talked about forming them in satisfying certain norms and formats. And even for data that isn't relational, that doesn't satisfy like SQL, is the strict. There are some types of NoSQL databases that exist but are also in a shape have a structure, not as strict of a structure, but have a certain structure. What happens when we have data that doesn't, isn't structured? How are we going to process it? When we talk about unstructured data, we genuinely talk about a mix of data. So we have different data types, different uh, formats that we need to process. One of the simpler examples that I usually use to illustrate it is something like if you have a group chat with some of your friends, on WhatsApp or Viber, Messenger, whatever you're using. If you dump all the data from there, you will have some videos, you will have some images, you will have voice messages, you will have a different texts, etc. That, and if you want to get some information from something like that where there's a big mix of data, that's unstructured data. So what are we going to use? What are we going to talk about? Well, as I said, we don't have a structured format, and that's most of the data that's generated. Global emails are another example, social media posts, etc. So if you are, trying to do something like sentiment analysis on Twitter to see like how people are feeling about something, you will have videos, you will have GIFs, you will have text. Links to outside materials, links to web pages. So it's pretty hard to just focus on a single. You can just process it as you would, a database where you have a table. So one of the main tools that we use when we talk about unstructured data, we need to process it. And usually the goal of processing unstructured data is to either display it somehow or get structured information out of it. So, for example, I talked before about sentiment analysis. Sentiment analysis is something that's pretty common with social media posts. For example, if a large company has an advertisement going on right now, they want to see how people are reacting to it, if it's positive or negative. So they will, filter the social media posts on Twitter or X, if you prefer to call it, and they will, check the hashtags that are related to them. So, for example, Coca-Cola might search the Coca-Cola hashtag, and they will have a bunch of posts, and they want to figure out whether the posts are positive or negative. To see if they are more positive than before they posted the advertisement, if there is more engagement, more meaningful engagement, etc. So you usually want to take those posts that are made by users and assign them some sort of a structured value. You want to maybe turn them into some vector of data where you have all the information. So you might want to say this user with this many followers posted this post. That had a certain sentiment and this many people watch it. So you want to turn it into structured data. You want to turn it into data vectors that you can enter into a table, a data set, or something, and further analyze. To do that, you will usually use something like NLP. NLP stands for natural language processing. Most famous example of natural language processing that most of you are very probably familiar with is ChatGPT, where you will just type in something and the computer will interpret that. Computer vision just stands for picture analysis, just using usually AI algorithms to determine what is the picture showing. And yes, usually it requires a lot of processing to actually get any insight out of it. And usually that process of filling, that additional information that is said, that's called metadata management. So to the post, for example, that this person has posted online, they maybe post an image or something, you will attach a ton of additional information. This information is called metadata. And that will, when stored, allow us to practically process information. So let's talk about the data warehouses. So data warehouse is a term that's used for structure, right? When I say structure, I don't mean a building. I mean a data structure that centralizes structured data. When I talk about structured data here, I don't mean in terms of a database. I mean in terms of we had unstructured data, we processed it, and now we are storing it. This is usually historical data because, as I said before, it takes time to process non-historical current data, so you can't necessarily do real-time analysis unless you have a lot of computational resources. And they are usually generated so you can actually go in the past and basically see what was going on, what was happening, perform analysis, and figure out trends that you can use going forward. That's the point of data warehouses. Each data warehouse is usually focused on a certain thing, a certain topic. Many companies will build data warehouses that are focused on them. And what the work is what they're related to. So, or even just a specific domain like their sales or, their sales in a certain sector, etc. They usually integrate, that's the point of a data warehouse. The difference between, a data warehouse and just a database. A database is usually used for something that you fill up from a single source, right? You have someone doing data entry, inventory information. Data warehouse specifically operates on different sources, which are different, heterogeneous, and those sources are processed to generate information that is stored in the warehouse. You can think of it like maybe you get different information that you're putting in storage, as you would in real life. If you're storing something, you will have you're putting stuff in the basement for storage. It may be your clothes, shoes, maybe an old bicycle, but everything will be organized in a way that you can access it, right? You will know. One of the things that are practically always noted in data warehouses is time. So we will almost always have an index of time. When some data was entered, or when that data was recorded, so you can track it. And one difference compared to standard databases is that you don't do updates. You don't change data in a data warehouse. If a sale happened, you don't update it. Data warehouses aren't meant to store data that you would update. So for example, you're storing sales data. If you're storing something like, okay, I have my own store online. I'm also selling stuff over Etsy, and I'm selling stuff over, I don't know, Amazon. And I'm building a data warehouse to track all the sales from all these different sources. All these different sources do different stuff. So, for example, if I'm selling on my website, I'm getting a nice CSV because I coded it and I'm selling that. But Etsy is selling me information through email that I need to process, and Amazon is I need to log into their dashboard and then programmatically get the data from there. So I will combine that and integrate it. But once I log that data and put it into, I made a sale, I won't necessarily update that. If I want to add information, I will add information as in a row. So for example, if something was a return, I want to count that as not a sale. I will just add a new table for returns, or just know that as a return, depending on how I formatted my data warehouse. So as I said, data is extracted from operational databases. Operational databases here simply means a place where there is data, right? It doesn't mean, a structured relational database. The process, that we are talking about, that I mentioned, is ETL. So we're talking about extract, transform, and load the data. This is what I just mentioned, where you have, different sales platforms that will inform me about sales in different ways. I will have to extract information about, I made a sale, some information about, where's this getting shipped to, what was the final sale price, and information like that is going to transform all of that information so it's structured, it's in the same form, and load it into that warehouse. So again, I'm transforming data so I could load it into the warehouse, which is a central repository, right, for any data that I processed. One term that you will commonly be mentioned here is BI. BI stands for business intelligence, and those are the tools that are very commonly combined with data warehouses, so they could actually visualize the data for upper management, CEOs, or something, some certain tier of employees that are essential decision makers and strategy planners, etc. In addition to data warehouses, we talk about data lakes. Why would you have data lakes? Because what data lakes, what do we have now? Well, in data lakes, we are storing unprocessed data. We are just loading the data, whether it's structured, semi-structured, unstructured, it doesn't matter. The benefit of data lakes versus data warehouses is that data lakes are fast. You don't need to think about anything. You're just loading the data onto a server somewhere. You won't necessarily be able to process that as easily as you would, structure data in a data warehouse, but it's much faster to store data that way. So the benefit of a data lake, when you're getting data out of the data lake, if you want to structure it, unlike a data warehouse where you have this ETL process that's called extract, transform, and load, right? This extraction and transformation of data happens when you're loading the data, right? When you're putting the data into the warehouse. So you are structuring the data on input. For data lakes, you aren't structuring the data on input. You are structuring it when you try to look it up. So if you have a ton of random files, let me continue with my example of, sales from different platforms. I would just have, Amazon sent me a PDF, Etsy sent me an email, and I have like a CSV file for myself. Great, I'll keep all of that there. And when I want the data, when I say, hey, I want sales for period, between June and July, June and August, I will, the processing will happen when I run that query. All the processing, all the analysis will happen then. If I'm storing some semi-structured data with metadata, that process might be faster, but it might be very, very slow. We have a lot of data that needs to be processed. Why do it even then? Why even have data lakes versus warehouses? Well, sometimes you can process data in time. Sometimes the data is just dumped in the lake, and because you aren't fast enough, you don't have resources to process it and put it into a warehouse. Essentially, warehouses will cost you more money because you need to do. There are two costs when you are talking about hiring computing resources. First is computing power, right? That's your CPUs. You're hiring CPUs. We'll talk about some cloud services later on, and you have storage. And it's much cheaper to get a server with a lot of storage but a weak CPU than a strong CPU with less storage. So easier. So basically, compute is more expensive than storage, and that's what happens here. So data lake, you can just throw data in there if you need it, because the truth is, you sometimes want to over collect data because you never know. Well, maybe we will want to analyze this 10 years down the line or 5 years down the line because we want to see how certain elements affected it. If we have that data, even if it's unstructured, great, we have it, we can run the analysis on it. But if we don't have that data, we can't do anything about it except maybe pay someone a lot of money to essentially give us that data if they stored it. And yes, there are companies that just work on storing the data and hoping they will need to sell it someday. So yeah, so that's the difference between, that's why data lakes are used instead of data warehouses. That's how we want to, illustrate it, and that's how we want to imagine a data lake is just, information is thrown haphazardly. You need to dig through it, swim through it to get it, while in a warehouse you have some structure. You also have data marts. That's something that I mentioned just now, which is, a data warehouse that's hyper focused on a specific domain. So you will have, specifically marketing values, something like how many people responded to our advertisements or our calls to action emails, etc. How did, what were the purchases, what were the purchases, if you're looking at from a financial standpoint, etc. This will allow you, a much faster access and much narrower access than having something, than having a massive data warehouse that you want to process for everything. When you have data that's connected to every single process of your company. There are different types of these data marts. Data mart will have those that are dependent on the central warehouse, or those that are standalone, or of course, as usually, there's always a hybrid of some sorts in any sort of structure. So, what's the difference between dependent and independent data marts? You can think of dependent data mart as something like a large chain of stores. I don't know which stores you have in your country. In Croatia we have Konzum. I'm just going to go. With America, we have a Walmart, right? You have probably heard about Walmart. So Walmart will have a central warehouse, and then they will send specific pieces to individual uh, distribution marts, basically different stores, and depending on what each store, depending on the region the store is in, and other information, they may send specific data in a certain way. Independent data marts are basically, a mom and pop, small market, a small store that will sell a specific item. So yes, so that's essentially the difference between a dependent and independent data mart. Dependent data mart is fed from a central warehouse. Independent data marts aren't, so it's easier to set them up, and sometimes you don't want to share information. Companies tend to be very sensitive about information sharing between certain uh, separate entities, within the company. So that's something that they sometimes want to avoid. They don't want to overshare information. Finances don't want marketing to know what's going on, etc. So that's sometimes why people separate fully independent data marts. In addition, I didn't mention it here, but there's another thing that I would mention, and you will sometimes hear the term called the data lake houses. So a combination between data lake and a data warehouse. That's essentially a combination of the two that uh, combines, combines basically both by having a data lake that allows you to, feed data into it quickly, and you can access the data directly, but at the same time, in the background, it's going to do that ETL process where it will extract and transform the data and load it into a warehouse, right? So you get best of the both worlds. Of course, the problem is the cost you need to pay for both, data lake and data warehouse computing and storage. But a lot of companies, that can afford it prefer that approach because they will have a data lake that collects all the data, stores it as is, and then slowly in the background, relatively slowly, we're talking about very powerful computers, processes the data and stores it, in a more formatted way. So I mentioned, extracting information, getting information. That's the process that's called data mining. Essentially, the point of data mining is I always try to illustrate it by saying you want to get this bunch of data points and show them in a way that's understandable, right? The difference between, when you're looking at pure data, it's like if you ever saw something like a nuclear power plant with a ton of measurements, with a ton of those, you have a ton of, I'm trying to find an image or something to illustrate it, but I can't. But basically, from the movies or anything, you have a nuclear power plant and you have a lot of measuring devices and stuff in the control room, and you have to look at each individual point. Okay, there you go. I managed to find something that works. Uh, so something like this. You have a bunch of these uh, measuring devices that will show you a bunch of different parameters, and you need to have people that know what's going on and what you're looking at here. And is everything fine? Is this value here okay? Is this value here not okay? That's complicated, right? We have a ton of data, we have a ton of numbers. Someone, this person here who has been trained and has the knowledge, probably has a nuclear engineering degree. Uh, they will, be looking at all of these values and they will know what it is, what are the good numbers, what aren't. But sometimes someone who doesn't, someone who is an economist, right, won't be able to. And that's okay for control rooms, right? But it's not okay for finances because the person who is making decisions, decision makers, your CEO or something, they probably don't have time to sit down and look at 10,000 different values and then make a decision. What you need to do is to essentially have something like this here. We have lights, green light is good, red light is bad. And your job when you're doing data mining is to basically figure that out. You need to take all of that data and pull out information. Are the sales good or bad? Are the sales worse than they should be, than what we are expecting by strategy and by realistic situation? If around are they worse than our competitors or not? That kind of information that you need to pull out. Here's one of the examples that I included. I mentioned fraud detection. For example, you want to know, if someone steals my credit card, based on just a few sales, you won't have someone at the bank checking every sale of mine, but you want, based on all of my sales and the ways I'm acting and the ways my purchasing history goes, if there is a sudden change in that, you want to raise a flag, right? You want to turn on the red light and someone will put a block on that card or contact me or check something. So what are some techniques when we're talking about data mining that we want to do? Basically, first is classification. That's assigning data into defined categories. And clustering is very similar. They essentially they both group data, but in classification, you already know what's going on. I already know that I will have positive and negative. You know the number of classes. For clustering, you don't know how many classes you may have, so you will just group the data and see what what's going on. The difference, for example, for classification is something like as I mentioned, fraud, fraud detection. Is this okay or not okay? We have just two binary classes, good, not good. Clustering, on the other hand, might be different types of, you know, uh, clients, depending on what kind of purchases they are making. Maybe we'll have a group of clients who are making a bunch of small purchases. If we are talking about, let's say, video games, you have microtransactions. You will have a lot of people who are playing for free, not making any microtransactions. You will have a bunch of players who will occasionally make a big purchase. You will have players who will often make small purchases, and then you will have like that whale group that is always targeted, which are people who are making big purchases often. And you want to group that and see, based on other information, try to extract, hey, what does this group of players that are spending a lot of money often, what do they like? What kind of game modes they like? What kind of stuff they're spending money on? So we can make more of that type of I don't know, loot crates or whatever. That's essentially association rules. We want to figure out what are the connections, and regression is when you are just trying to predict a certain value, a certain continuous variable. This is more commonly done in like engineering fields or something. I did a lot of this, for example, for internal combustion engines. You want to predict speed based on certain inputs. Especially, this is especially popular. It's not a big deal on a car, but for example, when you have a transatlantic large ship, vessel, you want to be able to predict what the speed is going to be based on different inputs, because you don't have just a gas pedal to control it. So that's something that regression does. It's usually more commonly applied in engineering and similar fields. Why? Because again, numbers can be complex to understand. You don't want to turn if you're turning 10,000 numbers into 10 numbers, that's great. But if you're turning 10,000 numbers into 10 red or green lights, that's better, because it's simpler to understand. Because not everyone will instinctively know. If I tell you, that's something I tell my students when they're doing AI, they will write something like, oh, I got an error of 0.56. Is that good? Is that bad? I don't know, because I don't know what the range is. I don't know if that's something that is perfect, or your range of variables is 1, so you are getting a 50% error. So that's something that again it's much easier to represent whether something is good or bad by using classification or clustering than getting an output number. When we are talking about some other processes that we want to do, we want to do data integration. So what is this? That's something similar to what you would do with a data warehouse. You want to get data from multiple inputs and show it concurrently, right? One next to the other. This is usually done in terms of dashboards, which will show, a ton of different information, something like this, where you have, different information, different classes. I know you talk about different types of graphs and stuff in data visualization, so I won't go over it. But basically, you want to integrate information from different sources into one single set of data that you can view at a glance, and you need to, do that, extract, transform, load on data. You need to virtualize data, transform it in some way, show it in the APIs. As I said, the APIs are application protocol interfaces. Basically, this means that you can communicate with an existing application in some way. So, for example, if Amazon has an API for my sales, that means that I can programmatically in Python do something like import Amazon.something something and access data. That's what an API is. Okay, so let's talk more about this ETL process. You have extraction, transformation, and loading. I talked about it before. So you essentially have data is gathered from various source systems. That's the first step, and is essentially put on a pile. transformation CleanSense formats data. Basically, you have a target format that you want to have. Maybe you have a data vector, a row in your target table that you want to fill out. And this process, after the extraction, collected the data through Amazon API about my sales, from my mail server, from Etsy sales, and from my CSV file, on my hard drive, from my local sales, for example. This will, go through each different data type that I have, and will say something like, okay, I need to fill information about how much was the sale from. I this type of input is Amazon API. I will do these steps to basically load that information. I'm loading it from a PDF. Okay, great. I will do it in this way. You don't necessarily have to have wildly different sources. For example, something that I worked on in the past was extracting data from patient reports that doctors write after a checkup, right? And different hospitals have different formats that you want to do. So some of them have a PDF that's essentially an image. Some have, nicely entered into a database, so you can just get the data directly from the database with SQL. Some of them have into PDF that's readable, so we can extract data. Some have PDFs that aren't readable, so you need to do OCR and figure that out. Essentially, that's the most complex part. Extracting is setting up, and we're talking about gathering data. We're talking about gathering data automatically. So I'm setting up connections, usually on a server somewhere, that's communicating with different sources and continuously collecting data. Transformation will then figure out what type of data collected, and will apply a certain algorithm, a certain program that they designed to extract all the pieces of information from the data that they want to fill a certain data vector, and then I will load that information. For example, it can be as simple as saving the information that I want into a CSV table, CSV file, comma separated values. That's what CSV stands for, if you haven't mentioned it. Yeah, so that's what we want. And now that once I have data in the warehouse, it's structured in a way I can now do further processing. I mentioned a couple of times metadata. Metadata is essentially context. It's a bunch of information. It's like an additional information vector that we can attach to data to give it context. The simplest example of metadata is if you go right-click properties on a photograph, or in some tools, you open the photograph, it's going to tell you this picture was taken at that date. These were the settings the picture was taken. Maybe it will tell you the location it was taken, which device the picture was taken with, and so on. That's something that can help us a lot, especially creation date, because different data, different times means different things. Data owner, data source, and when it's placed, it also means it can also influence that data. Where was the data collected from? Because maybe some sources are, we will trust certain sources more than other sources, etc. So yeah, so for example, if I'm looking for information about something from scientific journals, I am going to take a look at scientific journals that are indexed and published by well-known universities, and I will want to know that if I got data from there, I got it from a higher impact journal than like a self-published research somewhere on Arxiv or something like that. And wherever you're storing data, whether it's a data lake, warehouse, data mart, you won't attach a certain metadata to each piece of information you have, because it's going to be crucial in recreating more recreating information. We didn't talk about this in when we're talking about databases, because in databases, metadata will just be columns in your table, right? You won't have it attached separately. When I talk about attaching separately, I mean that you can have a file, for example, a video file, and then you'll have a text file. It will usually be denoted with like a same name but a different extension, and that metadata and that text file will contain metadata, or it will be something like a JSON or XML file, so on. Okay, let's talk about, I mentioned it a few times. Let me mention it again, data governance. It's always, people roll their eyes at data governance, but it's very problematic if you run into an issue, like you can get massive fines, you can run into serious problems. You can get your work essentially stopped by an inspection if you don't ensure that data follows the certain governance. So there are two levels of governances. There are regulatory governances that basically will make sure that we are following GDPR, we are following HIPAA, right? We are following ISO, we are following whichever higher level outside of our organization governance is being given. If a regulation is being given by our government or European Union or federal government in the US or whatever, that's one level of governance outside, and there you can have internal data governance, internal frameworks that define how you operate data. And this is usually a list of rules that the programmers will keep to allow them that when they're doing that, designing that ETL process, that especially the transformation process, will guarantee that all the data is stored in the same manner and complies to everything that we wanted to comply, that there are no errors and stuff. And if you don't have anything like that, basically what happens is long-term wise, your data starts falling apart. You will have less and less, your data won't be homogeneous, and instead of having like a nice structured data warehouse, you'll have something that's neither data warehouse, neither data lake, and you can even in some cases access the data properly because it's not listed as it should be. Okay, so let's talk, when we're talking about the term big data. Big data usually refers to high volume data, high velocity, high variety. What do each of these means? Well, high volume means there's a lot of it. There are a lot of, if we are talking about a table, if let's assume our data is in a table, we're talking volume, we are talking about how much each row, how fast we're getting, how many rows we are getting. We are talking about 10 rows, we're talking about 100 rows, we're talking about millions of rows of data in a table. If we're talking about high velocity, we're talking about how quickly are we getting that information. It's not the same to collect a million data points over 10 years or in half a second. And half a second isn't something that's improbable, for massive sales, doing like big Black Friday or flash sales at big websites. You will get hundreds of thousands of sales processed practically concurrently. And to complicate everything, you also have high variety. Uh, because if you know that everything you're getting is structured, that's not a problem. Because you can define one algorithm and you can then get some really good programmers on that algorithm, tell them optimize this, get out, break out C programming language, break out assembly if you need to, and write me an algorithm that is super fast for processing this type of data. But the problem is that you're getting hundreds of different data types because I talked before for an example, I'm selling stuff privately through my website, I'm selling through Etsy, I'm selling through Amazon. My CEO, if my CEO gets an offer and tells them, hey, do you want to come here and come here to, I don't know, Alibaba and sell your stuff to a Chinese market, they will jump on it. They'll be like, yes, awesome. And as a programmer in that sort of situation, I can't afford to craft this perfect algorithm for data processing from Alibaba, uh, because if my CEO comes to me and tells me, "Hey, I want data analysis on Alibaba," and I tell him, "Well, I'm still working on data processing from Amazon to make it super fast," uh, I will get fired. Uh, that's how it works in business. So that's the problem. You have a high variety of data, and you need to deal with that. You want to get a single nice data source. So that's essentially what we're talking about, and that's why data lakes exist, because we want to dump information and process it later on, because our algorithms can be so finely tuned to process it in real time. So we can process it overnight. We can process it with a delay of 1 or 2 days. Or a great benefit of data lakes is where we'll talk about cloud services, but you usually don't process stuff with your computers. You don't have servers in house anymore. You will have servers purchased from Amazon, rented from Amazon. So you have, oh, we wanted this faster, not a problem. Let's spend more money on servers in this short time. Yeah. So we can get that processing done. That's something that you can do with data lakes. There are specific frameworks like Hadoop and Spark to achieve this, to design this. These are commonly used to basically process information, and usually the king is machine learning. You mentioned that term before in previous classes. Basically, machine learning algorithms, once you train them, are insanely fast, and that's why they are very, very commonly used for analytics. Uh, because the only problem with machine learning is that you need data, and you have it in abundance when you're talking about big data. So yeah, we will talk about certain cloud data platforms that exist, like AWS. Will go into more details further when we talk about cloud platforms. So I will just, I mentioned it here, but we will uh, cover them in more detail if I'm not mistaken. Yes. Okay, so I mentioned the term data virtualization. What does data virtualization means? It's sort of a quick and dirty way to get a unified view of data without actually consolidating, without actually doing that transformation. And it usually refers to a set. It's not hard mathematical definition. Once we go into big data, we start losing those like precise definitions that we had in the beginning of these lectures. Now data virtualization is, it's something, it's a definition. It's usually used, to refer to something where you are trying to illustrate data in a, it's not a professional term, but it's a quick and dirty way. When you want to, okay, so for example, if I want to, I'm selling, I told you I'm already selling, like on Amazon, Etsy, and now I'm integrating Alibaba into my sales. Uh, I didn't have time. My CEO made a deal yesterday. We have already started selling. I didn't have time to learn to develop any sort of a program for uh, processing information from Alibaba sales. Okay, not a problem. I'm loading it into the data lake, and I'm going to process it in a day or two. But then there's a knock on my door. My CEO walks in and he says, "Hey, how are those sales on Alibaba doing?" And you're like, "Oh my God, I can give you an answer, right? Because we didn't process the information," and then you get fired. So, uh, what does the data virtualization do? Well, it's about finding a way to show that data, anyways. So it won't be as precise, but for example, what I can do is I won't have the exact numbers on how many dollars we sold, but I know that each time, I get a piece of information like a PDF for every sale that I made. So instead of showing how much dollars we have sold, uh, how much dollar value we have sold, I will show how much sales, as in the sales number we had. So I'm visualizing the money we made through sales because I can compare. Now, later on, that analysis can be shown to be a bit wrong, because, well, maybe I'm making a lot of sales, but on low volume, low price items, so that's not great. And I'm actually earning more money, off Amazon when I'm making a few sales of big ticket items. But for a quick and dirty setup, yeah, that's what data virtualization is. It's essentially transforming data from multiple sources to quickly compare them and offer an insight into that data. So the key here is this agile. You want to do it quickly and give some information in essentially real time while you're processing in a lake, while your data is stored in a lake or is being ETL'd into a warehouse. That's what we're talking about, like real-time analytics. We want to show data right now. And that's important in some instances such as stock market analysis, where you want to make sales now. If you notice, if you get information that the stock will drop, you don't want to get that information 5 days later. You want to get that information now and sell everything because your mathematical model has showed you that. This is very complex. It takes some real programming jobs to do anything real time, anything in real time, because you require a lot of processing and a lot of stuff. So it's very, very complex. I will mention now, just to end, we'll talk about data management, which is a part of the title here, data storage and management. What do you mean by data management? All this, are we storing the data in data lakehouse, data lake, or data warehouse? Are we extracting it into a data mart? Are we running real-time analysis or not? Are we virtualizing data? Yeah. So let me just clarify. I think I didn't necessarily mention it. Real-time analytics is different than data virtualization, because real-time analytics is doing like actual full analysis on full data in real time. So it's like the real deal right away, instead of virtualizing stuff to speed it up. Just to clarify that. Okay, so for data silos is when you have fragmented storage. It's usually you want to analyze data that's stored, but it's not stored properly. It's something that happens when like I mentioned before, you're structuring the data, but you aren't structuring it properly, and it starts to break down after a while because you didn't set up proper management, or even if you set it up, people who are in charge of storing the data didn't pay attention to it. Yeah. And then you end up with data silos that you need to process. Scalability is if your code works well for when you are, a small shop selling 20 items a month, it's not going to necessarily work well when you're trying to run analysis when you're selling 20 items a second. So everything, you need to worry about. If you're a computer scientist, you remember, you probably thought about the big O notation, which tells you, depending on the number, how complex this algorithm is in terms of how many times it's processing something. So this is that n in big O notation here will grow rapidly. It will grow to extreme values, and you will run into essential issues. Data quality is also another thing. You want to make sure, if you're filling a data vector, it's filled completely. You want to make sure that the data is accurate. It's real, because if you have spoiled data, if you have wrong data, you're basically spoiling the analysis that you are making. And finally, in the end, you also have the security for, as I mentioned, we talk about security a lot, for protecting, against data breaches and everything, whether you want to run encryption or not. Those are all certain information, because encrypting information, as I thought before, you want to encrypt information. Yes, in a database, when you're going to have 100,000 entries, but do you want to encrypt every piece of data? Because now, if encryption takes you half a second and you're getting a new entry 3 times a day, who cares? But you're getting a new entry 3 times a second and you need to spend half a second on encryption, that's the problem. Yeah. So that's something that managing, weighing security when it comes to big data. That's why you get computer breaches. That's why you have such stories like Sony losing a bunch of information on releasing a bunch of information on purchases by their clients because they simply, someone wait, oh, we probably won't get hacked. We don't have resources to do, to encrypt everything and do everything. That's kind of decisions that you need to make, and usually engineers get overruled here. So what are some, trends and future of data management? Trends essentially, AI, machine learning is growing and is getting more and more today. In the past, when you talk about big data, people saw it, AI, machine learning as a separate thing from big data. It's not anymore. You don't really do big data without some sort of AI, because AI is really, really good at processing data. Uh, as I said, combinations of lakes and warehouses into so-called lake houses is also growing, as well as, privacy preserving, because no one likes when their data gets leaked, when their data gets shared. And we will talk about, what the serverless mean. Serverless means that you don't have, you are using a server. Yes, you're always using, I think someone asked me on the last lecture, you mentioned cloud. Yes, a cloud is a computer. A server is a computer. It's no different than, my machine, that I'm presenting this from. It's just that it's, it's basically in context of use. My computer is here, is in the room with me. Server is in a different room. I'm connecting to it remotely. Cloud doesn't belong to me, right? I don't have access to it. I don't have access to the server. Uh, or I have a limited access, and it usually belongs to a big company as opposed to a server that. And I know that yes, renting servers exists, but usually when we're talking about server architecture, we're talking about in-house servers that we are talking. So we're talking about how I have 3 servers floor below me into a data room that I use for data processing and stuff. But for a lot of companies, servers take a lot of space. They take a lot of energy. You need to hire people to maintain them, to make sure they are all right. They are working. Servers break, right? Paying someone and using cloud, right? Using someone's service that someone hosting a service in cloud on their servers, right? That now the difference that these servers belong to me, cloud belongs to Amazon, right? Or Microsoft or whoever. And that's usually the price that you're willing to sacrifice, willing to pay, because you are making stuff simpler for yourself, and you don't have to worry about a bunch of things. So what's going to happen? What are some trends that are growing? We are looking at in the future that may happen with data management. First, structured, unstructured uh, is something that it's less and less focused on. We are just going to talk about data because, and this usually means that you get unstructured data, you will process it and make it structured, because less and less data is structured anymore. Less and less data is single source, and less and less data is when you're getting it from multiple sources, coherent between those sources. Another great thing is advances in natural language processing. ChatGPT is amazing. And just I'm using ChatGPT as a catch-all for large language models, LLMs. They are incredible. In the past, trying to get information, for example, I mentioned something like, a doctor's opinion on patient. Uh, Trying to figure out just whether the person is ill or healthy from a text, 3 sentences that a doctor wrote. That's something that I did in the past it was so hard to try to figure out what the person tried to say programmatically. You try using keywords, this and that, and sentences length, and order of terms, and this, and it was, and you would still get, very, very bad accuracy. Now I can take that and copy it into Llama or something. Essentially, I will assume all of you are familiar with what ChatGPT is. I'm talking about ChatGPT that's running on my computer or my server, so I don't need to, a version of a large language model such as ChatGPT. It's running on my computer. There are different ones that exist. I'm using Llama as an example. I can give it, that string and just tell it, hey, for the string that I just pasted, tell me, is this positive or negative? And it's going to be 99% accurate. Is the patient that received this diagnosis from a doctor, are they healthy or ill? And it will be 99% accurate versus 70% accurate. And it takes me nothing. It takes me zero effort to set it up and run it compared to, trying to analyze it algorithmically. It's awesome. Then we're talking about edge computing. What is edge computing? Well, edge computing is if I'm collecting data at a place, I want to process it at that place, right? So instead of getting, if I'm measuring, I have a device currently in my laboratory that's measuring the movement, the vibration of Earth to detect earthquakes and etc. That will essentially something like that, instead of getting the data and sending the raw data to me, and I will process it later. It's simple enough data that I can process it right there using the device, the Raspberry Pi that I'm using to collect the data. And then I can send the process data to me. That saves me time on processing thousands of data because I already get the process data saved. The problem is I don't get raw data. So if there is an error and I want to access raw data, I must hope that I've stored it there when I was processing it. And finally, you have automation using AI tools. That's mostly, classification, clustering, figuring out, hey, this input that I got here, where does it go? Which group does it fall into? You have clustering AI. It stores it automatically. You don't need to run different programming catches and try to figure it out. Okay, so this is basically, a summary of what we talked about. Essentially, what you need to remember about big data is that we're talking about when talking about big data, we aren't talking about data that's only large in volume, that there's a lot of it. We're also talking about data that's high speed. We're receiving a lot of it quickly, not a lot of it over the course of years. And we're most importantly, most problematically, it's varied data. It's not just pictures, it's not just videos, it's not just PDF that's formatted in a certain way, it's not just text that's formatted in a certain way. We are getting a lot of different things that we need to put together, and that's why we try to apply data mining and ETLs, processes, etc., to actually store the data so we can analyze it. And here's like the last point that I mentioned here is that data governance to and integration to actually store the data are critical, because if you don't set up rules, if you're ever in a situation, again, not of all of you are programmers, some of you are from medical fields, some of you are from economics. If you are ever sitting on, sitting somewhere in a meeting room and trying to figure out, insist as much as you can on getting good data governance, setting up proper rules, investing time into setting those rules, and thinking ahead of what could happen, having rules what happens for something that you can process, because if you don't, you're going to run into problem down the line. If you just say, "Oh, the programmers will figure it out," the programmer will do the best they can, but they don't have your knowledge, they don't have your domain specific knowledge, and they can't foresee possible issues. That's where you must come in, and that's where you must give your input and say, These are the rules on how we can store this type of data. Here's an example. If you're into medical fields, maybe you have encountered DICOM. DICOM is a format for different medical storage of different elements, mainly images. You're going to store image, but it's so much more. It stores metadata. It stores this. So, for example, for me, something like this, as a computer programmer, I'm going to say, oh, I don't need DICOM. DICOM is like 20 megabytes. I'm just going to use a PNG. I'm just going to extract the PNG, put it into the database. Bam! I saved 19 megabytes of storage for each image. It's for you, as a medical expert, if you're into medical field, to say no, we need a DICOM because DICOM allows me slicing. It allows me to store information about the patient. It allows me this. It allows me that. It allows me that kind of thing is what's crucial task for you if you aren't a computer programmer, and if you are one of those here who are computer programmers or computer scientists, and you find yourself in a position, don't let the people with domain knowledge blow you off and tell you, oh, you can figure it out. No, you can figure it out. Sit down with me, ask me, because it happened to me. It happened to everyone who does this sort of thing. You will do what you think is best. Like, for example, I said, converting DICOM into different formats, so you save space, and you will get into trouble 3, 6 months, a year, 2 years down the line, because you don't have information that you need, because you didn't even know it's possible. There are so many formats that just looking data formats that provide information, like feeds for astronomy, or I mentioned DICOM, ASSIG. I can talk about different data formats that you won't encounter, and you don't know how to process unless you have someone there who knows, who is the domain expert in that area. So that's, if you take anything away from this part of the lecture, take that away. Always work together with someone who knows what they're doing. And if you are someone who knows what they're doing in that specific domain, don't let programmers walk away without you sitting down and explaining it to them. I'm not talking about that programmers will, walk away because they don't want to hear about it, but they probably don't even understand that there is, something going on, some, additional information that may be extracted. Okay, and for the end of this, we are going to talk about cloud data storage and manipulation services that exist. Let me repeat what is cloud. Cloud is a server. Cloud is someone else's computer. Cloud isn't, nothing special. It's just a computer, that exists. This is, a well-known joke. There's no cloud. It's just someone else's computer. That's what I said. Cloud is just a server that exists, that is owned by someone else. It's hosting a service that you're using, and they are taking care of everything relating to server, right? What does that mean? That means that you won't have a situation like when my server died, because my climate control, my AC unit, right, went out of, it just broke. And I couldn't use my server for a week because I needed to get someone to come service the AC. We didn't know if anything was damaged because we couldn't turn it on, because it's a server that generates like 8 kilowatts of heat. We can't just turn that on without cooling because it's going to damage itself. And we know it ran for some time without cooling. And then, when that happened, like we lost some data because a RAID controller card died. So I need to spend like 2 times trying to 2 days trying to restore the data and so on. You eliminate all that problems by just going and saying, buying the server and compute time from someone else. There are issues, right? You can't always do it. You can't transfer some data like medical data freely to cloud services. You need to, get special permissions, etc. You don't own the hardware. From the parent perspective, if I say for example, the reason why we don't use cloud services in academia, at least here in Croatia, is because like when I'm getting funding, I'm going to apply for funding now, and I don't know how much computing am I going to need. So it's easier for me to say, like instead of saying like, hey, I might need 30,000 euros to spend on a cloud service somewhere, and then if I don't spend that, I'm going to, get negative points in the report because I asked for more money than I needed. And if I need more than that, oh, I'm in a trouble because well, I don't get funding for that from the project. But if I'm buying a computer, I can just buy a workstation now. 2 years later, oh, I need more power. I can just buy an additional CPU or an additional GPU, and just push more power out of the server that I have. So cloud, cloud isn't a be-all end-all solution, but for a lot of cases, especially large companies, just getting like a data center in a company, you will take a whole floor. For example, our supercomputer board, I actually asked Professor Tsar, who is the main instructor on this class, who helped me to come up with these lectures and everything. He was in charge of setting up the first supercomputer in Croatia, Bura, that is here in Rijeka. He's not involved with it directly anymore, but it was his accomplishment to actually bring it here. And and he told me that the expense, on just electricity is in the range of 15 to 20,000 euros uh, a month, right? So you can hire 20 people for that. Yeah, that's a lot of money to spend on just electricity, and you need to hire like 2 administrators to be there. You need to dedicate a lot of space to that supercomputer, right, or data center. So hiring is a lot of times when you put everything down on the table and you say like, oh, I need to rent a bigger building for my offices to enable that. I need to spend money on converting. I need to hire administrators. I need to hire some people who work on, on just like electrical support and stuff. I need to pay for electricity. I need to pay for this. It's much simpler to just hire what you need from the server, from a cloud service somewhere. We're going to mention some key providers. AWS, that's Amazon; Azure, that's Microsoft; Google Cloud; and IBM Cloud, right? So let's talk. AWS is the most popular one. So what I'm going to do now is I'm just going to go through this four, and I'm going to make note of some of their key services that they have, most popular services, etc. The idea of this isn't to teach you how to use anything or how to go. It's to teach you like, hey, these things exist. If you're ever in a situation where you are working somewhere and you need compute resource, and someone says like, let's buy, a mainframe, maybe you can suggest like, hey, I've heard somewhere that we can do this with AWS instead. Maybe we should look into it. So AWS is probably the most popular cloud platform. You will be amazed at how many organizations use it. It's incredibly well known, it's incredibly widely adopted, and basically, unless you have a specific reason that you want to go for Azure, Google Cloud, IBM, AWS is essentially default. There are a lot of services that you have. These are just some of them. These aren't even all of the services, and they focus on different things such as delivering applications to you, mobile support, specific enterprise applications such as, if you're in economics, you'll know better than me what this is, but for example, documentation and stuff, deployment, performing analytics, security, specific database services, networking setups. Yeah. So let's go over some that are key. S3, simple storage service. If you know what Dropbox is, S3 is basically that on steroids. It's essentially, like a Google Drive. You can upload things there. You're paying based on the amount of data that you have stored. And it has a ton of features: versioning, encryption, lifecycle. If you're storing data, if you know a company that is storing data, they are very probably using S3. You can use the Dropbox or Google Drive as an example. Of course, you can use this programmatically. You can write programs through an API that automatically connect, upload, download data, whether you want to archive data, whether you want to backup, whether you want to do content delivery. So you can push data to Amazon for people with download of S3. And as I said, the main benefit of this is pay as you go. Depending on how much storage you have there and how much you're using, you're paying exactly for that much storage. You're not paying for 100 terabytes if you're using 1 terabyte. If you're using 1.4 terabytes, you're paying for 1.4 terabytes, right? That's what is amazing for companies. EC2 is elastic. So as I said, I mentioned before, usually when we're talking about renting cloud, hiring compute units, we're talking about either storage or compute. Storage is storing data, not processing it. EC2 is processing data, running computation, doing anything. Elastic Compute Cloud is basically you connecting. If you are like running a simulation, you can connect to this. This is a computer, right? Server somewhere that you can connect to, and you can run your simulation. Nothing more than that, right? It's as simple as it is. But the key here is elasticity. It's elastic. It means that if I am running something that's really, really complex, I'm going to pay more. If I'm running something that's simple, I'm going to pay less. And that is great because you can actually optimize what you want to use, how much you want to spend, how much money you want to spend, and you don't pay. Like you aren't hiring time at a supercomputer somewhere. You're not hiring like a month of compute time on a supercomputer when you don't know. Maybe you're going to need more. Maybe your computation is going to be done in an hour. With EC2, you don't have to worry about that. You can just toss the calculation on there, pay as much as you want, pay more if you want it done sooner, if you're using parallelization, pay less if you want slower computation. It's completely up to you. Glacier is storage, but it's very, very slow storage. It's when we talk about storage, we talked about hot, warm, and cold data. This is glacial data, right? It's very cold. I think I've heard something about them using magnetic storage for this. I can't confirm if that is true, but basically it's data that you aren't like with S3, you aren't going to access now like you would of your Google Drive. You're going to say like, hey, I needed this data. It might take you a few minutes. It might take you a few hours to get it. It's slow. It's not immediately available. Why? Because it's kept offline, right? If it's kept, I don't know the exact way it's done, but if it's kept on a magnetic drive, that magnetic drive isn't plugged in the whole time. They probably have like a robot or something that's going to actually go and plug in that magnetic drive, load the data or onto a hard drive, and then send that data, expose that data to you through something like a S3 service for you to access it. Right? That's what Glacier is, and it's really, really cheap. Like you can store. Let me check just the pricing. Let me see if I can find it. You could no, they have moved to you can request pricing. Sadly, I hoped that you can get something that you can get an actual price, right? But okay. Uh, Sadly, sadly I can't find it, but it used to be extremely, extremely cheap. You could save terabytes of data for couple of dollars. It's probably more expensive now with everything, inflation and etc. But you could save terabytes for dollars a month, right? Relational database services, again, specifically created so you can throw an SQL database on there, and it's designed. When I talk about this is a service, it means it's designed. It has an interface that you connect to, and it allows you to set up everything that you need about an SQL. So yes, you can connect to it like I showed you with SSH. With you can use a terminal like this to connect, but you can also use any web interface to connect and do stuff. DynamoDB takes care of NoSQL. I mentioned Dynamo when we were talking about like key value pairs, etc. But basically that's another service that exists if you want it. And Elastic Block Storage is essentially storage for EC2 instances. It's also elastic. It's like S3, but it's elastic because if you're using elastic computing, you might, if you increase compute usage, you might increase data storage usage. So you might want to use EBS instead of E3. And finally, oh no, we have more. So we have Redshift for data warehousing. That's their data warehousing service. And again, the benefit of this is like if I talked about, oh, I went the wrong way. All of these services are designed to interact one with another, right? So when I talk about, using something like Redshift for SQL querying data warehousing, the benefit of this is that it's designed so it can really, really easily integrate with Glacier for storing data or EC2 for calculating and running ETLs. That's what is the benefit of using something like an AVS. All of their services are designed to work nicely together. Lambda is a compute service. If you need something like not like an EC2 where you're going to run a lot of information, you're going to run something that's complicated. This is for automatically running in response to events. Like you get an invoice in your computer, it will automatically run code that will extract data from that invoice and forward the invoice to an appropriate person, right, or something like that. Again, scalable, cost-effective, billing is based on execution time. That's key when it comes to these services. Another example is Microsoft Azure. Azure has a number of different services. Blob storage is for storage of text and metadata, right? That you can just throw on there. You also have disks that are block storage. I used the term block storage before. I didn't explain it. If you don't remember it from the file systems, when I say block storage, is just storage that you are used to, like your hard disk drive. So that this is again Google Drive, something like that, an equivalent to S3. Azure also supports SQL databases through Azure SQL Database and something like Cosmos DB for NoSQL, so instead of DynamoDB. Sometimes this will direct you towards Azure versus AWS or something else because, hey, Azure supports the specific database type, NoSQL database type that we are using for our application. So it's easier to integrate our current, server stuff with Azure instead of AWS. So that's the reason why you sometimes might select Azure versus something, one versus the other. It enables, data lake. Synapse Analytics is interesting because Microsoft is very focused on business application in terms of like if you're an economist, in terms of like management, C-suite operatives, stuff like that, business analysts, that sort of workload. That's what Azure is focusing on, as opposed to Amazon, which is much more general when it comes to what they are targeting. So Azure will focus on something like that. One of the tools that they are using is Power BI, which is their tool for data visualization, and they offer great integration with that. All right. Another player in this area is Google Cloud. You have probably used some of stuff that's in Google Cloud through just osmosis, Google Docs, Google Drive, Google One. It's simpler, it's smaller, but it has a lot of great services. So cloud storage is something that you have used it in this class when I shared information. It's just Google Drive on a much larger scale. You can automate it. You get, unlike with Google Drive that you need to access through your browser or through an app, you get API access, so you can program data submissions, backups, and stuff to cloud storage directly without like, oh, I'm putting in a folder that gets updated. You can just update it automatically. The benefit, of this is that you can integrate stuff with other services like AI services. BigQuery is just the SQL querying for large databases, and similar to SQL querying for data sets, etc. And integrates a lot of tools that Google has. The main benefit of Google as a cloud provider is that they have a massive amount of like small tools and services and stuff that you have that will enable you to like target specific type of data. So if you have something that's very specific, you're processing a specific type of data in government, like making decision where to go to, Google is worth looking into to see like which exact services they have, because they have a bunch of small extremely targeted services. Okay, so cloud storage, NoSQL document database, right? They are usually integrating this with mobile apps for Android. A lot of mobile apps use Firestore for storing, their information when they're working. If you're using any apps that store things, on Android, they're probably using Firestore if they're a bigger app. So Spanner is a relational database. It's very interesting because it's aimed at being globally distributed. So if you need a database that is accessible, we have clients in one of the companies here locally that I work with. They have clients in Japan. They have clients in here in Europe. They have clients in United Arab Emirates, China, Japan. They are actually using Google Spanner for their database service as a basis for their database service, because they want what Google Cloud Spanner does. It automatically spans to where you need it, right? So it will enable a person who is from Japan to access it on a server in Japan. A person from America is accessing it on a server that's there in America, and that enables very quick access to the data. And it assures that all the data is the same everywhere across the world, etc. Then we have, IBM here. IBM is less popular. It does work, but it's not really as popular. One of the main benefits of it is this IBM Watson, which is mainly focused for AI and machine learning. Although today it's not that popular as Google is, or Amazon especially. So yeah, another thing that I want to mention, there are hybrid cloud storage solutions. What does hybrid cloud storage solutions mean? Well, many organizations use something that's called a hybrid storage, where you have some of your data stored locally, some of your data stored remotely. For example, let's say I don't generate a lot of data, but I do a lot of computing, but I don't do a lot of computing often, right? Maybe, let's say I have a lot of employees and I need to calculate payroll for them once a month. And they have, I don't know, 10,000 employees. That takes a lot. That's great. Example, for me using, I have a complicated payroll system. And I would need to buy like 10 workstations, put them in a cluster to calculate that in a day so I can deliver paychecks to people. That's a great example for is something like Elastic Cloud Compute, because once a month I can just hire some resources, throw it on there, calculate what I need, get the data back. That I don't need to have a Glacier and S3 and everything. I can store all of my data for my employee payroll locally and just integrate that local storage with cloud storage. Not just cloud storage, but cloud compute, right? Uh, or another example is I have, like for example, I do a lot of machine learning here. So if I have a company that does a lot of machine learning, maybe I want to keep the data for the projects that are current on my local storage, but actually store a lot of older data like automatically throw it first onto S3, so it's accessible, but it's online. So it takes a bit of time to access, and then automatically move it to Glacier storage. If it has been, 3 years since that project has passed, I'm not probably going to use it again, but I don't want to throw that data away. So those are some examples that you can use when you're talking hybrid, and of course you can talk about like hybrid in terms of you can use Azure, combine it with AWS, because as I said, maybe Azure has your CEO really wants to use BI, for display and dashboards and stuff. But your engineering department really wants to use AWS because they like the services there. They they need like a Dynamo or something. So you can actually create a hybrid that combines Azure and AWS, right? Finally, yeah. So what are the main points of using uh, cloud data storage and manipulation instead of going locally? This I already mentioned that, so I'm just going to go over this. First, scalability. You need more, you pay more. You need less, you pay less. That's great. You don't have to worry. You don't have to go. If I want to, like such a thing as I want to add more storage here. Oh, I need to, in the simplest terms, I need to call someone to sell me some drives. I need to talk to them. I need to ask them, like, hey, how much are you selling this drive? That might seem high, so I'm going to contact someone else. Then I'm going to tell them, okay, sell me 10, 20 terabyte drives. And they're going to tell me, oh, okay, we'll deliver it to you in 3 days. And it comes here, and I need to get it installed, but my admin is on vacation, so it can be installed in the servers and configured. So I need to wait. So he comes back, deals with tickets, and 2 days later he installs the drives and sets them up. And it's been 20 days for me to get 200 extra gigabytes of storage. While with cloud, I can do it immediately, right? I can just I just go into my dashboard and say I need 200 terabytes more. Bam, I go to 200 terabytes more. Uh, I'm going to pay for them more per gigabyte, and they aren't here. They're in the cloud, etc. They're negatives, but they're available to me right now. Again, cost efficiency. I mentioned that a lot. You only pay for what you're using. Reliability is also king, simply because Amazon is taking care of that. If an Amazon server dies, I don't even notice it. Even if I'm like connected to it right now, thanks to virtualization and some other techniques that exist, you can literally be working on a server, it physically dies, it physically falls apart, and you won't even notice because you were automatically moved to a different server. And it's done so quickly that you genuinely don't notice. I'm not talking about like there's a small, crack or something, and you ignore it. No, you just don't notice. It's that good, and that's something that something like this provides you. While compared to if your server dies, do you have another server? You probably, I mean, it depends on the size of your organization. But if my server dies here locally, I'm done. Until I repair it. Okay, and finally, security, security encryption, end-to-end encryption for sending data. Let Amazon carry about that. Uh, I need to make sure that European Union has decided that all data needs to be encrypted. Oh my God, I need to go down to my server. I need to set up DOS again, configure it so everything is encrypted. I'm going to add so much time to my calculations and processes. Oh God, I'll just let Amazon take care about that. 6 months later, after then I've done all that work, the European Union decides that, oh no, we want not only do we want it encrypted, we want it encrypted for a specific algorithm. I have to do all of that again with something like, if I'm using AWS, I don't have to worry. In most cases, Amazon will take care of it. So finally, in conclusion, cloud data storage will allow you manipulation. basically modern enterprises at the scale that they exist wouldn't be possible without AWS, because there would be so much overhead, so many issues, that you would dedicate so much time to just fixing errors that happen. Because when you have someone like Amazon can operate at an extremely large scale, and that extremely large scale allows you to have something like have hot spares of a ton of servers that can just be ready to go. No organization can do that, and if your bank, probably uses AWS, your bank, if their servers go down, you can't get your money, you can't do anything, and that would be something that's much more common because servers die. Servers are, they're computers, they're physical objects that just break, and AWS allows you to using AWS or similar cloud service enables you to just be automatically moved. Your whole service automatically moves to a working server, and you keep going, keep working. No one notices that except the people who are working there. The cost of certain operations simply wouldn't be possible without elasticity in hiring storage, and of course, so that's why cloud is super super important today. Uh, and that's essentially it with this we end this data storage and management class. I will probably see you in the coming 2 weeks with some elective classes, so I hope to see you there. We have all the links and everything for connecting. If you have any questions about that, feel free to email me. And that is that. So thank you once more for joining me here and listening to my rants for the last 10 or so hours. And I hope you have learned something useful. Okay. Thank you very much. We're done with this class.
Thank you. Goodbye. Bye bye.
Bye bye.